Okay, good morning, Dee. Sorry we're not doing this live. Perhaps this might make it a little bit less glitchy than it has been today. Unfortunately, I cannot make it to lesson today, so I'm going to record this for you so you can watch it through instead. This is really to get you ready with some of the key ideas, the little bits and pieces that make the chapter work. So we're going to look at basically the large bulk properties behind materials to start off chapter 2. Now for you, the actual main starting point will be the practical this week. So I've posted the practical for hooks law, single spring and a series spring, a longer spring joined together, and two joined together sideways to make them in parallel. Those will actually make you understand the ideas of what's going on when you combine it with the stuff we're doing here. Okay, so the chapter is really about materials, but because you know Hooke's law, we can start off with that place to get it going. So what we're going to do is the start of chapter 2, section 1 is all about the kind of properties behind the scenes. So there are three things that we're going to cover, which are basically density, they are pressure, and just to link it back in then, so you can see the link for it, into last chapter with upthrust. Okay, so those are our key things. All of those have equations. All the equations come from a reason, and it's that reason that's really, really important. Now, I'm going to run through some bits on the way as well, just to make sure we're all happy with it. So to start with, those ideas need to be really, really clear in your head. So we have an idea of what they represent, okay, which is what we're going to look at when we talk about the materials, but their actual definition of what they are is something you need to learn and get right for the exams. They're worth marks in the exams, so you need to make sure you're happy there. So the first one is density, and if I just put it up out of the way, because we're going to use it all the time, density is defined as how much matter you've got. So density is mass of material per unit volume. Okay, and that's the correct way of saying it. It could be a meter cubed, it could be a cubic centimeter, it doesn't really matter too much, but it's the idea of how concentrated the mass is, how much mass you've got within a certain space. So definition wise for us, it'd be kilograms and it'd be meters cubed. So I'll put that over here just to remind you. Okay, now from that we can define an equation, and the equation is useful, saves us writing a lot, but the equation means this, it's the definition that's there. So the symbol we use for density is rho. Okay, at GCSE you might have used D, but hopefully you've used rho, and it is literally mass over volume. It's a capital V for volume and a lowercase m to be really specific. So those ideas is telling us quite a lot about the materials, and when we think about mass and where it is, we can then start to think about why it behaves in the way it does, that material behaves in the way it does. So an example might be a classic example with bread. If you throw on white bread onto water, it will sink. Even when it gets a bit soggy, it will still sink. So even though it's gaining particles, it's increasing the amount of particles within it because it's taking in water. The density of those particles, the closeness of those particles is still less than the water, which is why it floats. But if you take your bread, you fold it in half and then squash it down so it's the same thickness, where you will have the same mass but in half the volume, which means that that density has got twice as big. And even if you just fold it in half, it's probably dense enough to be more than water and will sink. If not, fold it again, squeeze, and it will definitely sink. So that idea of how things behave, for example, surrounded by other fluids like water, means that it will depend on the density of the actual material itself. So the idea of the atomic spacing. And when we get into materials, a lot of the properties of how materials behave is to do with this idea of atomic spacing and atomic structure. Okay, so that's a kind of a key thing. It's not just an equation. Now, from that means that certain objects, because they have mass, or have mass because they have density, and because they have mass, that then starts doing things. So if you put, for example, an object in your hand, you'll feel it because it's pressing down. So it's the property of the matter itself which gives it things like weight. So that steals us into quite a lot of different areas. So we have our weight. Because of weight, it also gives us pressure. Okay, so the pressure under your feet, for example, is because of your, as we said in that last test, because of your weight and because how concentrated that is. So the pressure exists because of your density. And we can also then start thinking, and again, it actually relates as well. That relates into there, and these relate into the idea of upthrust. Okay, which is really important as well. More important than you think. So we'll pick up on that in the last part of this lecture today. So big ideas, all linking together through this. So let's see how. So first idea, pressure. Well, pressure is the kind of thing that happens underneath a substance because of all of that weight pressing down upon a certain area. So that area underneath, where you've got your mass, will create a pressure. It will press down on the substance. How it presses down, we can go into more detail because there's a more technical term than pressure. But it's because it's made of particles that it press down, but the particles wouldn't press down unless you had gravity as well. So the weight is mg, the force downwards is going to create pressure on the ground, but likewise the ground will then press on the substance, so there's pressure back. So pressure is what's happening in the gap. Now for what we've got, it's a nice simple idea in that what we can call static pressure. Again, gives us our definition. It's the force per unit area. Okay? Pressure is force over area. Okay? It's not the idea of how concentrated the force is, because that's just an idea. The definition, the actual thing that defines it and therefore gives us an equation, is the force per unit area. Cross-sectional area if you prefer. There's two different ways of doing it, but keep it and then we can get the equation. Now that's fairly obvious with a solid, okay, but solid is not all materials. Materials can be gaseous, they can be vapors, they can be plasmas, they can be liquids. Anything, general term-wise, anything that's not a solid is known as a fluid. Okay, so we'll talk about fluids in general because they all mix in the same way, but they behave slightly different because you can't press down on a substance with another substance in quite the same way. And why? Because the particles inside behave differently. Okay, so they're still dense, but when you have liquid, density changes. So if you were to take, for example, water, and you were to swim down into the bottom of the tank of water, what you'll find is that your ears will pop more and more and more. You'll feel the pressure on you. If you try swimming down, for example, with a hose pipe in your mouth, you'll only get around about a metre down before, even if it's a strong hose pipe, that will be crushed by the pressure from the outside, so you won't get any air through it. And the further you go down, the more pressure there is. Now, in a swimming pool, that pressure isn't because the particles are more dense at the bottom. Okay? In the ocean, where you're talking about several kilometres, then yes, that's more realistic. The pressure will change, even over hundreds of metres. But if we're talking about relatively shallow stuff, then it's not to do with the density. The density is nice and steady. Okay, so that doesn't change. But what does change is how many particles are pushing on you. So this idea of pressure increasing due to force, well, the force is because there is basically more water pressing against you. It's more concentrated. So why is that? Well, it is a simple idea in that something like the substance I've just taken away, the solid, presses down on you, Well, liquid is pressing down on you as well. You have all this air, all this fluid above you, and all of that is pressing down on you. Now, it's also around you below here as well, because the particles move in all directions, it's pressing on all directions. But yeah, how much it presses is literally down to this column of water above you. And so, you know, that column existing on you has a certain weight. Now, I know there is more here, and if it's the sea, for example, then obviously you have a lot of weight at that level. But what you'll find is actually it's just that vertical column of area that is the same as you. So again, it links into this cross-sectional area. So let's just prove where it comes from, and more importantly, show where the equation comes from that's in the data book. So if we take a substance, again, we'll go for a nice cubic shape. Just makes it a little bit easier to get your head around. The pressure comes from being at a certain depth. Okay, there's a height of water above you. Now, we use H because actually you feel pressure when walking around. People get more headaches due to the high pressure on a high pressure day. Okay, if you take a flight and you go up into the air, your ears will pop as it bends the eardrums in. Okay, if the pressure is greater, it will press the eardrums in. If the pressure outside drops, then what will happen is the air trapped inside your ear will bend the eardrum out, and that will hurt more and more the more it bends until you gulp, and that equals up the pressure on each side, and so your eardrum will no longer be pressed in one direction. So you are at the bottom of a sea. It's a sea of air. Now, it won't make as much difference as diving down into water because the density of water is much, much bigger. Okay, the density of water, I got the other class to estimate, and we came up with various answers. Some people remembered that for 1 centimetre cubed, okay, one tiny little centimetre cubed, you get 1 gram. Now, that depends on the temperature, because when you heat things, they expand. So it's only got certain densities at certain temperatures. Other people had Googled it when I asked them, and they came up with 993, I think it was. Again, it depends on the temperature. So generally, at room temperature that we are at the moment, and possibly a bit cooler, not too much hotter, definitely, the density of water would be 1,000 kilograms per meter cubed. Okay, metals are around about 7,000. Rock is around about, it depends on the time, but again, around about 4,000. Liquids, they're not a lot less than that. Yeah, so sorry, that one is a liquid. For solids, they're not a lot more than that. So don't change a great deal for the type of substance. So water, solid is slightly more than 1,000. Okay, slightly more dense. But if you heat steam and it changes into gas, all the particles spread out, and so the density is less. Now, before we move on, most people remember that as grams per centimetre cubed, as I say. So what I want to just pick up there is a lot of people, again in their test, were doing the same things, struggling to work out how many zeros to add or move the other way. So how far does your decimal place move about? So how do we get that? Well, if you go from 1 gram per centimetre cubed, we just need to know very simply how many centimetres cubed there are in a metre cubed. And I had lots of guesses. A lot of people were saying 1,000, a few said 10,000, some said 100. All of them were way off. It's way, way bigger. So how does that work? You could try to guess. That's where it goes wrong. So what you need to do, and like with the area of your foot question, you need to convert it first and then do the maths. So all information makes more sense if you can get it in the right scale. So here's a cube that is a metre in all directions. So that's a cubic metre, 1 metre cubed. 1 centimetre cubed is around about that big. Okay, so it's a tiny, tiny corner of it. Now, how many of those, even if you draw it, it's quite hard to guess. Some people come up with, say, 10,000 or 100,000, but again, they're still wrong. The way to do it is think in one dimension. So how many centimetres in a metre? 100, yeah? So this is actually 100 times bigger than a centimetre cubed. Height-wise, it's 100. Width-wise, it's 100. So to get your 3 dimensions, you cube that linear dimension. So in other words, 100 times by 100 times by 100, okay, which is 1 million. So there are 1 million centimetres cubed inside a metre cubed. Okay. To do this more scientifically, and I'm going to do this in a colour that shows up better, if we are thinking of the conversion, well, if I wanted that centimetre as a metre, in metres, then it will actually be 0.01 metres. Yeah, and using the same method, if I go to 0.01 cubed, well, what I'll end up with is 0.00000. Well, let's do it in standard form. You'll end up with 10 to the minus 6, or a millionth. Okay, again, playing with powers and indices. Another way of doing that, 100th is 10 to the minus 2. So 10 to the minus 2 times 10 to the minus 2 times 10 to the minus 2. You add the factors together, the indices together, so it's 10 to the minus 2, 4, 6. It's 10 to the minus 6. Or, for those that like their maths complicated, that's cubed 3 times 2. Again, 10 to the minus 6. Okay, so that is the value of that in meters cubed. Okay, really common mistake to avoid. Just convert it into meters or into the appropriate unit and then stick it into your equation and do the maths. So let's just go back to that. So that's 1 million of these. So if I had 1 million centimeters cubed, well, I'm going to have 1 million grams. And if we have 1 million grams, then, grams, then that is 1,000 kilograms. Okay, so multiplying that by 1 million, we multiply that by 1 million, million of them is 1,000 kilograms, 1,000 kilograms for every meter cubed. Okay, so that is what I mean by fluency with maths, being able to do the maths and throw it around a little bit. But really common mistake, do not try and guess where the zeros, where the decimal place or how many zeros there are. Okay, so moving back to this. Density of gas is that if you swim down about 10 centimetres, that is around about the same change in pressure as climbing up 100 metres in air. And the reason is that for water, for that, it's 1,000, whereas the density of air is around about, again, it depends on temperature and pressure, on average 1.2 kilograms per meter cubed. Okay, so 1,000 times smaller than that one. Okay, so you'd need to go 1,000 times the distance in air to get the same popping of your ears as a 1 meter in water, okay, or any distance in water. So, what does that give us? Well, if I just come back to that one, move that out of the way, okay, I want to work out the pressure here. But what I need is effectively, it's the weight, as I say, of that volume above us. Okay, so I need that weight of water. So if we do the maths of it, I've got a bottom there, pressure equals mg, force over area, okay. M, well, I need to know the volume because I will need the volume and density to get the mass. Any question you see in the exam with density, where they give you the density, they're nearly always wanting you to work out the mass. Okay, so that's a really important trick. Remember that when you're spotting it. In the exams, density, work out the mass. Sometimes, really rarely, they might want you to work out the volume, but it's usually the other way around. They want you to work out the mass. So what I'm going to do here instead is I want to change the mass. So I am going to just get rid of those and save that. Convenient version, density times volume. Okay, that doesn't seem to be showing up very well, so I will do that in red instead. So mass equals rho V. Now, put that into there, I'll end up with rho V, equals rho V times G, okay, because that's my mass, divided by area. Okay, now that volume is going to be area times height. Yeah, so I can put that in as rho area height G, so that's instead of V divided by area, which fairly obviously cancels out because it is the same area, the area of the box and the area, cross-sectional area of that column above the box. So what we end up with is an equation that basically says that H rho G is the way it's written on the data book. The pressure of a fluid or in a fluid varies with the height of fluid above or the depth of fluid that you're in. It depends on the density, hence 1,000 times more pressure in water than in air. And it depends on gravity. So if they're not being pulled down as much, you won't feel as much pressure. So some planets, if you're in liquid, there won't be as much pressure pushing on things. So that's known as hydrostatic pressure. Okay. And it's all right, I'm recording. The hydrostatic pressure is to do with the depth of liquid above. So if you, for example, buy a waterproof coat, for example, it will tell you the height of water that if you put on top of the material, you can get before there's enough pressure for the water to be pushed through. Okay, so very, very common thing. Let's just put that in. So hydrostatic pressure, and that is in the data book. So that is P equals H rho G. And what you've got going on there is when the particles are just moving around and it's just all stood still. There is another one that we're really not going to go into. We will go into more depth next year because we need to look at pressure in fluids much more closely. There's a lot more we can do with it. But basically, that other one is hydrodynamic pressure. It's the idea that if you have, for example, a wing, very bad wing, the pressure on the bottom, and therefore the total force on the bottom, needs to be bigger than the pressure on the top. And it's that pressure difference that causes the wing to be lifted up. It causes flight to happen. Okay, and that's because it's all to do with the air flowing past. And if the air is flowing past faster, it's pushing less on the surface. So it's, you know, part of it is about wind speed. But we don't need to go into the maths of that. That's really quite complicated. So pressure in fluids, okay, and in liquids and in solids all comes back to this idea of density. Now we're going to look at an idea that's very similar. We're going to call it stress, and we'll come back to that why. But it's all to do with forces. So we are in this substance, this example, we are pressing down on it. So we are compressive forces. We have compressive pressure, pressing. But we also have tensile, where we stretch it. So when we do the Hooke's law experiment, we're doing the same thing, but instead of pressing down, we're pulling down and stretching it out. So we have tensile forces instead of compressive forces. But the maths is exactly the same. It's changing the density in the material, which is where we're then going to link that all together. And the effect is the same. You're going to get a feeling of pressure pressing on something or pulling away from something. Now, to round it off, we can link this into the last part, which is, if we, the last part of the last chapter, is that this also gives us this idea of upthrust. Now, again, this is much more in the PowerPoint, so there's more nice pictures, etc., etc. But the idea is that when you have things that are in a fluid, what happens is, because of the pressure pressing in not being the same, what you'll find is that the difference between them causes it to be lifted up, but it needs to be surrounded by particles. Now, that's the same with you. You at the moment are surrounded by air, and so because of that, you are actually lighter or feel lighter than you truly are. Okay? If we were to sit you on some bathroom scales and we were to suck the air out of the room in a true physics way, what you'd find is that you would actually get heavier. Your scale reading would get more because the air is holding you up a little bit. Okay? Now, what that means is that even things that are in the middle of water, okay, for example, things floating, they don't have to float to the top. If anyone's got an Archimedean thermometer, you'll know about it because it floats at different levels. But this can be floating underneath the water, and even it could be sitting on the bottom. It's still less weight. Correction. It doesn't feel as heavy as when it's not being surrounded by the fluid. So if you've ever picked anything up off the bottom of a swimming pool, anything really heavy, or in the sea, and you go, that doesn't feel too heavy. As soon as you lift it into the air, you realise it's a lot more massive. It's a lot more heavy than it felt. It hasn't changed mass because it's the same number of particles. Okay, be careful with your language. Getting the sun coming off the floor, so I apologise if this is a bit bright. What we're going to do, if I tell you what, let's turn it a bit there. Let's get a bit more darkness, I think, over here. So what we've got is our particles doing this is what causes the pressure difference, and then the reason is this part of it is deeper than others, but it also links into density. So I'm going to bring them all together. Now, just to make it clear for density, if you had seawater, maybe density of around about 1,012 kilograms per meter cube, something like that. If you had something else in the water that had exactly the same density, it would float at exactly the same level. Okay? If it was less dense, it would float higher up. More dense, it will float lower down. Okay? So that's the basic idea, and it will find its level according to that idea of pressure. So let's go back to the cube. Okay, so we have a cube. Again, it's a cross-sectional area A, and it's floating in a substance, let's say water, perhaps. And what's happening is, because it's a certain distance down, okay, and because it has a certain height, so that's level there, the bottom of the box, the bottom of the cube is further down, so there's further pressure. Because there's a difference in pressure, you end up with that lift being created. So, can we do the math? Nice and straightforward, actually. Now, just before we do that, we need to clear up some things. So, we're going to talk about the density of the water. Okay, just to make clear. So, not the density of the object. It does have density, but I'm not worried about it. We're going to take this idea of how much water it's floating in, because it's the water that lifts it up. So if you think about that, then that density creating the pressure depends on the depth. So at this height here, the pressure, let's call it pressure 1, that's going to equal the height or depth of water, so in this case D, times by rho of water, and gravity. Okay. At the bottom, exactly the same, but pressure 2, same equation, but you've got that extra height which I haven't labelled. Let's call it H. Okay. So what we've got here is we've got D plus H gives us that total depth times by rho G. Okay. Now, if I want to find the pressure difference, delta is often used for difference or change. So pressure difference is simply the second one subtract the first one. That's how we find the difference. Okay, so they're always that. Often worth putting that, I'll just say, when you're doing maths, it's easy to put that because it makes it always work. And a lot of people go wrong because they miss the obvious step. So what I've got is that, subtract that, and you can do the steps in the way if you want. But if you take d rho g and h rho g, and you take away d rho g, you're just left with h. So that's going to be h rho water g. Okay. Put that there. So pressure is that. Okay. But what I actually want is the force. So at the moment, I've got mg down. Okay. I want to know how big from the centre I've got upthrust. Okay. And the reason I've got upthrust, as you'll see in a second, is because I don't have any water there. There was water before, but the water's gone. So that missing weight helps. Okay. So let's just go with this, but I want to find out a little bit more. Density is there. So the density of the water depends on this mass that we've just done in reverse. I'm just going to flick it in reverse. So if I take H, that's going to be the same. So that's the height of the box. I want the density, which is mass over volume, and I've got my gravity. Okay. But the volume of this box here, or this, sorry, the space that the box has now filled, so the water that was there, well, that is the same as H mg over area times by height. So area of the box, height of the box, and so those cancel out. So we basically end up with mass over area. Okay, and that's going to be giving me the pressure difference. But I want a force, so I'm just going to leave that there. I should tidy it up. I want to keep it simple so I can fit it on your screen. I want the upthrust force, so I'm going to call it force up. Okay, so force up. That is going to equal pressure times area. Okay, and if my pressure is this, and I will now use the tidied up version, equals mg times by A divided by A, obviously that disappears. So I have a mass, I have a gravity, but it is not the mass of the box, it's the mass from the density of water, it's the mass of the water that's missing. So effectively, upthrust here, I'll put this in at this point, upthrust equals the weight that's basically gone missing. The weight of the displaced liquid, I should say, or gas, displaced. Okay, so the fact that you've taken away some weight, because there was weight there, that missing weight is now pushing upwards. Obviously it isn't, but mathematically it is. So the weight of the missing water, the weight of the missing particles is what's actually creating the up force. Okay, which means that it doesn't matter what you do on there, the upthrust will change. So if you had something floating and there's a little bit of force on the top, it's going to float quite high up. If you put more weight on it, you need more upthrust, so you need more depth, and it's all going to go a bit deeper. So the mathematics of it might be a little mind-blowing, but it's really just sticking three equations together, you know. However, the idea that you get out from it is really, really important. it gives us all this idea of how everything that we think about and how things behave with matter, materials, in this case the water for example, is all to do with the density. So density is not just an equation, it's a really big idea. Okay, so there is a section in the notes. I've put it as a walkthrough so you can get that off YouTube, but that's the background ideas. What I want you to do is start with this idea of how things behave, Hooke's law, and then we're going to link it to the density and therefore the material inside, the material that it's made from. Okay, so have a go with the questions. I've not managed to see any, obviously who's involved and stuff. So when you've had a look at this, can you just give me a quick, yeah, okay. I'm going to put it on the channel so you can pick it up and you can just give it some likes. That'd be good. I'll get the register off that, or just send me a message. If you have not yet got your practical in, the practical into OneNote to do with the two diagonal strings, like thus, lifting up, and your unknown weight lifting down, as they say. If you've not got that written up, you need that in, because I'm now going to jack it up to the next level, and that is starting to think about how you lay out your practicals. I want much more analysis on graphs and the main bits to do with how you lay out your data. Now, just to give you a heads up, so jump away from this. Some people with their experiments, some people's write-ups, they had their results like this. Second one. Third one. And they just written them in. And when you've got half a page of this, you cannot see any patterns. This is not the standard needed. You need to tabulate the data. Not only do you need to tabulate it, but you need to put it into a table, tabulate it, but put it in order, either getting bigger or smaller, doesn't matter. But then you can look at it straight away and you can see anomalies, you can see dodgy results that need retaking, or you're just seeing the pattern straight away, so you know what your graph should look like. So it's an easy double check. So please, please, please make sure you get your data right. And fairly simply, the basic principle is whatever you are changing, whatever your independent variable is, that's going to go on the left. Okay. Now I show this in the YouTube video, so I won't go into a great deal of detail, but what I'm after is your dependent variable for the first experiment. Normally, in a lot of difficult experiments, we will then repeat that. So we'll call it dependent 1, dependent 2, whatever it may be. It might be length 1, length 2, length 3, distance moved 1, distance moved 2, etc. So we need the proper titles. And then at the end, we'd have our average. Okay. However, for this, it's a static experiment, it's not moving, so it's quite easy to, especially freezing the videos, dead easy to get the results in a nice structured way. It took me a long, long time to do it, so spend time thinking about how you write it up. Okay. For this one, I want you to, similar idea, first experiment, second experiment, so second set of springs, third set of springs, okay? They will all be, because I've done this carefully and I think about these things, they will all have the same independent variable, okay? So they'll have the same load on the springs. So some will stretch more, some will stretch less. But that's your key thing I'm looking for to start with. Don't forget the units. So again, slash in watts, in newtons, in meters, in kilograms, in whatever it is. Okay. For this one, it's going to be load, but again, it's in the video. So the other key bit is you will end up with a graph with 3 sets of results on. Don't do 3 graphs. Okay. Big graph, fill the page, And when you're coming in next week, you can collect paper. So if you want to leave the graphs till then, by all means, but get the data in there ready. And what you need to do is you find your 3, and I want you to find the gradient, a nice big triangle, always a nice big triangle. Don't do little ones because you'll find that the numbers they give out are wrong. Okay, so you need a nice big triangle, and that will be your change in dependent variable, which due to a bit of jiggery pokery, it is true that you can have change in force, and you can have your change in length, which we call x, has a particular term, so you can have your stretch, and that will give you a value of spring constant. So I want you to get into the habit of analysing graphs. Again, it's in your sheet, it's in your data book, it is in the book I've given you, so it's in the module 1, the one with science in strange letters on the front. There are about 8 people who haven't got this, 9 people I think who haven't got this, so it is also in module 1, you can have a look. But there is a bit on how to use the gradients to get your graphs. Okay, so in section 4, it's got about analysing data and so on, and plotting graphs. There is section 3 is the table stuff. So look in there, make sure you're doing it up to the standard, and that's what I'm going to be marking you for. I want to be able to get those ticks for your evidence for great skills in graphs and tables. Okay, the one after this will be a first full write-up. So I'm going to look at other things like risk assessments and stuff. But hopefully we'll have a bit more time to do that because we're looking at how we can get more people in, so you may be into college more frequently. Something to look forward to. Okay, going to leave it there. If you've got any questions, do fire them through to me on Teams, or if it's more general, then just post it in the Year 12 channel and see what comes back to you. Yeah, a lot of people there. Help out. You are all in this together. We've got a long journey yet, so just help each other to get their heads around stuff. Don't give them the answers, but give them some help to kind of support it through. Okay, thanks very much, guys.